In this video, we're going to check the following series for convergence and absolute convergence. Now, for convergence, we can see that we have an alternating series here. We have the alternating piece. So really, all we need to check is the limit as k goes to infinity of ln of k over k squared, and see if that decreases to 0. Well, this is an infinity over infinity case as is, so let's use L'Hopital's. So we'll take the derivative and we'll recalculate our limit, and we'll have 1 over k over 2k. So simplifying, we got limit as k goes to infinity of 1 over 2k squared, which we can see is going to go to 0. So it turns out this is a convergent series. Now to check for absolute convergence, we need to first look at the absolute value of our series. So negative 1 to the k, ln of k over k squared. Basically, that's going to eliminate this alternating piece, and so really the series we're looking at is k equals 1 to infinity of ln of k over k squared. Now, we need to see if this is convergent, and what I'm going to use is the fact that ln of k is less than the square root of k for large values of k, and it turns out even for k greater than or equal to 1. Now, if we're not sure of this fact, there's a way we can test this as well. And I'm going to do it off to the side here. What you would do if you weren't sure, don't want to take any of this for granted. We're going to look at the limit as k goes to infinity, and we're going to look at the ratio of these two. Doesn't matter which one you put on top or bottom, so maybe we do square root of k over ln of k. If ln of k grows faster, this is going to go to 0. If square root of k grows faster, it's going to go to infinity. If they grow at the same rate, it's going to go to a number. We have an infinity over infinity case, so that's going to be L'Hopital's again. So we get the limit as k goes to infinity of 1/2 k to the negative 1/2 over 1 over k. So we have the limit as k goes to infinity of 1 over 2 times the square root of k times the reciprocal here, k over 1. These are going to simplify, and we're going to end up with a square root of k on top. So limit as k goes to infinity of square root of k over 2. Clearly the numerator grows, the denominator doesn't. So that goes to infinity. That tells us the numerator grows much faster over time, and that square root of k is larger than ln of k for large values of k, which is our hypothesis there. This is important because now it's still true if I divide both sides by k squared. Well, let's think about what that series is. We have the series from k equals 1 to infinity of square root of k over k squared. That simplifies to k equals 1 to infinity of 1 over k to the 3/2. This we know is convergent by p-series, and so it follows that this series is convergent by the comparison test, which means the original series is not only convergent, it is also absolutely convergent. So that's how we can show absolute convergence.